Hello everyone, I'm Anik Momtaz from Michigan State University and welcome to my talk on predicate monitoring in distributed cyber-physical systems. This is a joint work with Niraj Basnet from Oregon State University, Houssam Abbas from Oregon State University, and Borzoo Bonakdarpour from Michigan State University. When we talk about cyber-physical systems are essentially computer systems that have integrated software and physical components that ideally seamlessly interact with each other as well as the environment around them. A particularly critical class of cyber-physical system includes applications that are distributed over a network of nodes, also known as agents. Some examples of safety-critical cyber-physical systems would be health wearables, a network of medical devices, a fleet of drones, a fleet of autonomous vehicles, and so on. So as you can imagine, the difference between a functional and a non-functional or unverified safety-critical cyber-physical system could potentially translate into life and death scenarios of their users. Cyber-physical systems, or rather distributed cyber-physical systems, have three characteristics. The output signals are always analog, which means they're continuous time and continuous valued. Each agent has a local clock that is subject to clock drift from the other agents' clocks, which means that each agent has their own clock, and this clock could deviate from one another by a certain degree. And three, distributed cyber-physical systems obey the physical laws and dynamics that can be used to predict their behavior. For example, let's say we have two aerial vehicles and we want to make sure that they don't collide with each other. So if we know the dynamics, or rather if we know their acceleration and deceleration values, then not only can we predict not only can we say whether or not they're colliding with each other in the current time, we can also sort of predict whether or not they might be colliding in the near future when we know the values of their, let's say, position and their acceleration, deceleration, and so on. So cyber-physical systems come with their own set of challenges. Let's say, for example, we have a signal X and signal Y from two different agents, and we want to monitor the safety property for all time instances X is strictly greater than Y. So if we overlap X with Y, we can see that yes, indeed, X is always greater than Y in this case. Or is it? Because let's say that X for some instance got delayed by a certain degree. And if that happens, then since they don't share a global clock, the same local clock values for the agents may refer to different moments in time. So let's say that now that we know that maybe there is a difference in time, let's try to align X and Y again with respect to the global time. Once we've done that, let's try to overlap them again. And in this case, we see, oh no, there is an intersection between X and Y. So X is strictly greater than Y no longer holds. So as you can see, the lack of synchrony may eventually lead to inconsistent monitoring verdicts. So in this case, exhaustively exploring a distributed cyber-physical system and verifying all possible behavior in most cases is not possible at all. Furthermore, due to agents typically communicating with each other through, let's say, messages or signals, additional constraints on the event ordering are usually imposed. So for motivation, we're interested in monitoring distributed cyber-physical system by applications in automated air traffic controls, or AATC in short. The Federation Aviation Administration, or FAA, in the United States is considering a federated framework in which analog signals like the position and the velocity of aircraft must be monitored by the AATC tower software to see whether or not they violate or satisfy certain safety properties or predicates. For related work, when we talk about centralized monitoring, for most of the centralized monitoring approaches use a shared global clock and are completely oblivious to the system dynamics. Whereas when we're dealing with decentralized monitoring approaches, most decentralized monitoring approaches use pure discrete time for ordering of discrete events. So this discrete event ordering is good, or they work for pure software systems, but they're not sufficient for cyber-physical systems. So our contributions in this work is, first of all, an SMT-based algorithm for centralized monitoring of partially synchronous distributed analog signals for predicate violation or satisfaction. And we propose a retiming technique that sort of compresses and stretches time to find these predicate violations or satisfactions in question. And then we propose a lightweight mechanism for incorporating bounds on system dynamics to reduce monitoring overhead and by extension improve our performance. And finally, we provide an analysis of the sensitivity of monitoring overhead to the clock skew bound and the amount of communication between the agents. Coming to the model of computation for our work, let's talk about predicates first. In terms of runtime verification, we want to monitor predicates over a distributed cyber-physical system. Predicates are essentially Boolean expressions that are defined over simultaneous states of different cyber-physical system agents. For example, let's say if we want to monitor mutual separation clauses between all pairs of agents, then the corresponding formula could be that the distance between every pair of agents would be greater than or equal to a certain given threshold. Let's take a visual example here. So let's say if we have our clock skew epsilon at 5 and we have two separate drones at point A and point B. And these two drones from T1 and T prime 1 travel to T5 and T prime 5. So just from looking at this, you might be able to say that, okay, since they're at T5 and T prime 5, maybe they satisfy their mutual separation clause. However, since the clock skew is at 5, it could be possible that one of the drone is reporting time that's different than the other drone, and maybe the drone is in fact within our given mutual separation threshold. So our work works under certain assumptions. For example, the first assumption would be partial synchrony, where we say that for any two agents, the clock value that we read from these two agents will always be less than or equal to epsilon, which is our maximum clock skew. Furthermore, we say that our agents are always deadlock free, meaning that the agents being analyzed never go into a deadlock state. Now we'll talk about the happen before constraints. In every agent, we say that the events are totally ordered, meaning that for all t and t prime, if t is less than t prime, then et must happen before et prime. Furthermore, if E is a message send event, and if that message is being received by event F, then we can say that E happens before F. Then for any two events, if we say that T plus maximum clock skew is less than T prime, then ET must happen before ET prime. And finally, the happen before ordering follows the transitive properties. So if E happens before F and F happens before G, then we can say that E happens before G. Now we're going to talk about consistent cut. Given distributed signal, a subset of events C must be a subset of E is said to form a consistent cut if and only if C contains an event E and then it contains all events that happen before E. So formally we can say that for all events that is in the set of events, if E is in C and if F happens before E, then F must be in C. For example, in the figure to our right, we can say that if our epsilon is 0.1 time units, then C is a consistent cut. However, C prime is not a consistent cut. So our solution is an SMT-based monitoring algorithm. The features of our solution is that there is a central monitor that solves the monitoring problem at a fixed interval, receiving input from all the adjacent agents. The monitoring problem is transformed into an SMT solving problems, and therefore whose components are modeled as an SMT entities and SMT constraint and solved afterwards. And finally, signal retiming. So as signals are measured using their respective local clocks, the monitor needs to align them to detect possible violations and satisfactions. And this is done using a retiming function. A quick example of a retiming function would be, let's say we have two signals X and Y, and we want to find the retiming of Y on X. And we do this by using a function that compresses and stretches Y so that Y eventually intersects with X. And if such an intersection is found, we want to use that the function for which this intersection is found is our desired retiming function. More formally, our retiming function will always have to be an increasing function, such that for all t, the difference between t and the retiming of t must always be less than our maximum clock skew. And then if we have an event ET that happens before event ET prime, then T must always be less than retiming of T prime. So now we're going to talk about the SMT constraints. So the first SMT constraint that we need to find is finding a local time T and S at which point our given predicate phi is violated. And we do this by finding some T in some interval I1 and some S in some interval I2 such that signal X is a piecewise constant, signal Y is a piecewise constant, and S is a retiming of T, and then the predicate violation phi must hold. The next SMT constraint we want to ensure is that we want to ensure that rho is an epsilon retiming from I1 interval 1 to interval 2, or interval 2 to interval 1 rather. And we do this by saying that for every S in interval 2 there exists a T in interval 1 such that retiming of S is equal to T, and the difference or time difference between T and S is less than our maximum clock skew. And we call this our interval constraint. And then we have the constraint for our retiming function, and we want to ensure that the retiming function is increasing. And we ensure this by saying that for all S in I1 and for all S prime in I2, if S is less than S prime, then retiming of S must also be less than retiming of S prime. And we call this the increasing constraint. And our final constraint is enforcing the happen before relation for the message transmissions. And we do this by saying for all T1 and T2 in interval 1, if T1 is less than T2, then rho of T1 must also be less than rho of T2. And we call this our happen before constraint. Now we're going to talk about exploiting the system dynamics. So physical processes in cyber-physical systems follow certain laws of physics. And we can use these laws of physics, or the knowledge of these physics, to leverage our CPS dynamics to make the monitoring more efficient. For example, if we have our signal X and Y, and if we know that X will always be greater than or equal to 3 and Y will always be less than or equal to 0.5, then we can significantly reduce our search space so that it eventually makes our runtime much faster. Now we talk about the case studies for our work. So first, we used a network of ground autonomous vehicles, and the data was collected using two 1/10 scale autonomous cars competing in a race around a closed racetrack. And the cars were using Wi-Fi antennas to communicate with a central monitor, and the signal length ranged from 1 to 2 seconds, and the clock skew ranged from 1 to 5 milliseconds, and the predicate we were monitoring was the mutual separation predicate, which is the distance between the two cars would always be greater than or equal to a certain threshold. And our second case study was data collected from a simulation of a path planner software for unmanned aerial vehicles performing various reach and avoid missions. And the signal length in this case was about 2 seconds. The clock skew ranged from 1 to 5 milliseconds, and again the predicate we were monitoring was the mutual separation clause, which is the distance between every two pair of agents would always be greater than or equal to our given threshold. Now we talk about the experimental results for our case studies that we have conducted. So first we're going to talk about the impact of segmentation. So by segmentation, what we mean is we chop our work into multiple segments and we assign these work to multiple cores of our multi-core CPUs. The goal of this approach is to divide the work and eventually end up reducing the runtime. As you can see from the graph to the left, when we have a lower number of segments, when segment count is 0, meaning there is no segment, the runtime is really high. But as you do more segment counts, the runtime becomes lower. However, if we do too many segment counts, let's say at segment count 20, our runtime goes back high again. And this is mostly attributed to the fact that when we do the segmentation, we need to create new SMT instances. And the work needed for creating these new SMT instances eventually overshadows the benefit that you get from doing the segmentation to begin with. And we can see the similar results for the network of UAVs as well. And now we're going to see the impact of clock skew. As you can see, for both networks of cars and networks of UAVs, when we increase the clock skew, that doesn't increase our runtime by that much. However, again, when we do more segmentation, our runtime gets slower, and when we do fewer segmentations, our runtime gets higher. Now we talk about impact of communication. So for this experiment, we started off with our epsilon at 1 millisecond, and then we went up to 2 seconds. And as you can see, the epsilon has a drastic impact on our runtime. However, there is no correlation, or there is no noticeable correlation between the number of messages sent and received between the messages and the runtime. And this applies for both the UAVs and the cars. Then now we talk about the impact of agents. So we start with agent count 2 and we go up to agent count 10. So as you can imagine, agent count 2 has a lower runtime. However, increase in segment count doesn't really help that much in terms of runtime when the agent count is really low. However, when the agent count is higher, increasing our segmentation has a drastic effect on reducing our runtime. And on the right, you can see the best runtime that we can receive for each number of agents. Now we talk about exploiting the system dynamics. So as you can see from the graph to our left, we have the velocity profile of two cars, car 1 and car 1 denoted by the blue graph, and car 2 denoted by the orange graph. And we have the runtime, which gets lower when we do the velocity profiling as time goes on. And then on the right, we have the comparison between the SMT for the normal runtime and the SMT for the dynamics runtime. And as you can see, that the dynamics runtime is much lower than the normal runtime that we have normally received. For conclusion and future work, we want to find all global states that satisfy or violate a predicate, not just one state. And we want to monitor distributed signals with respect to signal temporal logic, or STL specifications. And finally, we want to extend our solution to a decentralized distributed monitoring solution in the presence of fault, meaning that we want to have a fault-tolerant solution and a decentralized monitoring solution. And that concludes my talk on predicate detection of distributed cyber physical systems. Thank you for listening.